Here's your bonus multiple choice review video for Chapter 10. Number 1. Anne claims that a store brand fertilizer which works better than homemade compost as a soil enhancement when growing tomatoes. To test her theory, she plants 2 tomato plants in each of 5 planters. 1 plant in each planter is grown in soil with store brand fertilizer, and the other plant is grown in soil with homemade compost, with the choice of soil determined at random. In 3 months, she will harvest and weigh the tomatoes from each plant. Which of the following is the correct confidence interval Anne should use to analyze these data? So is it a 2-sample problem? Is it a paired interval? Is it a 2-sample Z interval versus a 2-sample T interval? B was a paired Z interval versus D is a paired T interval. Or E, the correct interval cannot be determined without the data. Now, what we have to really determine here is, are they really making this a true 2-sample problem? Or are they somehow pairing these 2 different fertilizers together here? And so what we really need to kind of look at is how they're doing the tomato plants. Now, if they had said, we're going to have 1 tomato plant completely in 1 planter and 1 tomato plant completely in a separate container, and then the difference between the 2 would be that one would have the store brand fertilizer and one would have the homemade compost, then I would say that's more of a 2-sample problem. But they said they're going to plant 2 tomato plants in each of the 5 planters. So they're putting these 2 tomato plants in 1 pot, essentially, where half of the pot has the store brand fertilizer and the other half of the pot has the homemade compost. And then she's going to harvest and weigh the tomatoes from each plant. So the 2 tomato plants that are in the 1 container are being paired together in a planter. And so she's wanting to look at the mean difference of these tomatoes. So she wants to see, under all these similar conditions that are affecting the 2 plants per planter, they'd be getting probably about the same amount of sunlight, they'd be getting the same amount of water, versus if they were in completely separate planters, then I would say that would be more of a 2-sample problem. So I would gather that this is some sort of paired problem. Now, is it a paired Z interval or a paired T interval for a mean difference? Well, then we have to consider, did they give us the population standard deviation value? And nowhere in here does it say we should use, sigma to be approximately this much. So it is not going to be any type of Z interval, but it is a T interval. And we said it wasn't going to be a 2-sample, that it was more of a paired T interval for a mean difference. So the correct answer here would be D. Number 2. The weights in pounds of 3 adult males are 160, 215, and 195. What is the standard error of the mean for these data? Well, the standard error of the mean in our confidence interval formula, if I had x bar plus or minus t times s over the square root of n, the standard error is the last part of the confidence interval. So we need the sample standard deviation divided by the square root of the sample size. So I need to get the sample standard deviation. So if I put these numbers into a list and then I went and ran 1 variable stats on that list, I would get that the sample standard deviation, the SX, comes out to be 27.84 approximately. And that's where sometimes people will go, oh, look, the answer is B, there's 27.84. But we still need to divide that by the square root of our sample size, so we need to divide by the square root of 3. Then that is truly the standard error. That's how much a quote-unquote standard deviation is worth to this particular problem. And in the end, whenever I divide that out, I would get 16.07 as the standard error. Now, if the problem asked, what is the margin of error? Well, then we would have to take that 16.07 and then multiply it by the t critical value, and then that would give us the margin of error. Number 3, you want to compute a 90% confidence interval for the mean difference in height of mothers and their adult daughters using a random sample of 30 mothers who have an adult daughter. What critical value should you use for this interval? Well, this is a paired t-interval problem. And it's paired because the mother and the daughter are a pair together. So this isn't a two-sample problem. We're not looking at, a sample of mothers versus a sample of daughters that really have no relationship with those mothers, but they are being paired together. And so if we wanted to do a critical value, the critical value is going to be in this scenario, a t, because they didn't give us the population standard deviation to use up here. So we're not going to use a z interval, but a t interval. And so therefore, to get that value, we're going to have to use inverse t. For a 90% confidence level, that means there is 10% in both tails, and therefore 5%, 0.05, of area left in one singular tail. Now we also have to do the degrees of freedom, and the degrees of freedom was just the sample size minus 1. So sample size 30, degrees of freedom would be 29. So when I type that into my calculator, I get approximately 1.699, which would be, very close, answer choice D. Number 4, you want to construct a one-sample t-interval for a population mean using data from a population with unknown shape. In which of the following circumstances would it be inappropriate to construct the interval based on an SRS of size 14 from the population? So population distribution, unknown shape. We don't know if it's normal. We can't use that. Sample size of 14. Can't use the central limit theorem, so we're going to have to rely on option 3, which is we need basically to look at the data graphically to be on the lookout for strong skewness or outliers. So that's what they're wanting us to focus on in number 4. So a stem plot of data is roughly bell-shaped. Well, that's okay. That doesn't have strong skewness or outliers. And again, we're trying to find the one that is inappropriate. So A works out. B, a histogram of data shows slight skewness. Slight skewness is okay. C, a box plot shows the values above the median are much more variable than the values below the median. Now, this is a very awkwardly worded statement here, but basically what they're saying is that you have a box plot. So imagine we would typically see something like this, right? But they're saying the values above the median, here's the median, are much more variable. Now, when they say more variable, we're going to think of that as spread out. It's more spread out than the values below the median. So what they're saying is if we went median and then we really spread out those values above, that below the median, they're not nearly. Right, when it says much more variable, that's meaning that there's a lot of skewness in this. So this would not be appropriate. Basically, they're using a very awkwardly worded statement to describe strongly skewed. Now, D, the sample standard deviation, that would be our S, or in the calculator SX, is large. Well, we don't need the sample standard deviation to be large. We really need the sample size to be large, right? Now, so that really doesn't make it inappropriate if the sample standard deviation is large. There is no criteria on whether it should be small or big or any value in between. So this is just kind of like a dumb answer. It's not inappropriate. And the sample standard deviation is small. Again, who cares if it's too big or too small? That really has no bearing on whether we should do a confidence interval or not. All right, number 5. A 95% confidence interval for the mean mu of a population is computed from a random sample and found to be 90 plus or minus 30. Which of the following could be the 90% confidence interval based on the same data? So notice we originally started off with a 95% confidence interval, and now really the only change in the problem is we are going to decrease our confidence level because they're saying based on the same data. So All of our data is exactly the same. So the sample mean is going to be the same. The sample standard deviation is going to be the same. The sample size is the same. So if you think about our full formula, x bar plus or minus t times s over the square root of n, they're telling us if it's the same data again, this is the same number, this is the same number, this is the same number. The only thing that's going to change is that t critical value. And so if we decrease the confidence level, then we are less confident, and that meant that we didn't have to go out as many standard deviations. If we wanted to only hit 90% of our data instead of 95% of our data, then our confidence interval will be narrower. So we need to find an interval that would produce a narrower result. And so this is the same exact one. These, we're really focusing on our margin of errors here. These are going to be larger, aka wider confidence intervals, and 21 is smaller than the original 30. So this is the only one that would be narrower. Now, is it going to be 21 exactly? Well, it says could be, right? And we don't know what the sample size is because some people might be going, well, we can go ahead and figure out what this t critical value is. But you don't quite know what that is without the sample size because you would need degrees of freedom to go with this. So in the end, we can't actually calculate what that t critical value is without the sample size. So that's why they're going with this could be the correct confidence interval. Number 6, do high school seniors with part-time jobs spend less time doing homework per week on average than seniors without part-time jobs? For a random sample of 45 seniors with part-time jobs, the mean amount of homework time is 4.2 hours, with a standard deviation of 3.8 hours. For a random sample of 45 seniors without part-time jobs, the mean amount of homework time is 5.8 hours, with a standard deviation of 4.9 hours. Assuming the conditions are met, which of the following is the correct standard error for a 95% confidence interval for a difference in the population means? So again, this one's asking about standard error. This is a two-sample problem. We're looking at the difference in two population means. And so if I wrote out the entire confidence interval formula, I'd have the difference of my sample means plus or minus the t critical value times the standard error. And that would be this. And this would be a formula. The standard error part will be given to you on the chapter test because it's on the AP Stats exam formula sheet. So really, you just need to plug in the correct numbers into this formula. Now, one thing to note, even though that we're always taking the difference here, we always add these individual standard deviations. So automatically I know, hey, that's not right. Hey, that's not right. And E doesn't look like that at all. That looks like, I don't know, kind of like a one sample with a two sample combined in there. So now B versus D, notice they both have the correct sample sizes in the denominator. They're both squaring something, and they're both adding the individual fractions there. But where are they getting 4.9, 3.8 versus 5.8 and 4.2? That's where they're talking about the sample means versus the sample standard deviations. We need the standard deviations. So with a standard deviation of 3.8 hours, with a standard deviation of 4.9 hours. So we need these values to be 3.8 and 4.9, and B is the one that correctly does that. So they were actually using the sample means, x1 bar and x2 bar, in that formula, which would be incorrect. Number 7, few people enjoy melted ice cream. Being from the sunny state of Arizona, Megan and Jen decided to test if generic vanilla ice cream melts faster than Breyers vanilla ice cream. This problem is sponsored in part by Breyers vanilla ice cream. Doesn't melt that fast. At 10 different times during the day. Sorry, that was a commercial on there. The girls put a single scoop of each type of ice cream in the same location outside and timed how long it took for each scoop to melt completely. When constructing a paired t-interval for a mean difference using these data, which of the following distributions should Megan and Jenna check for the normal condition check? Now, at 10 different times during the day, so their sample size is 10. So they don't tell us anything about the population being normal. With a sample size of 10, we can't use the central limit theorem. So we would need to see a box plot or a box or two box plots. It depends on which type of problem we're doing. If we're doing a two sample problem, we would need to see two box plots, one for each type of ice cream. If this is a paired problem, then we only need to see one box plot. Now, they were nice enough to tell us that this is in fact a paired problem. Why is this a match pair? Well, because at the same exact time, they put a single scoop of each type of ice cream in the same location outside and timed how long it would take for each scoop to melt completely. So they were pairing together each type of ice cream at the same time using the same conditions. They weren't just going outside, and doing just Breyers and seeing how long it took, 10 separate scoops and then going somewhere else, or even could be the same location and doing 10 scoops of the generic ice cream. But they were wanting to pair up a scoop of each type at the same time in the same location and time to see what the difference was in how long it took one to melt versus the other. So this is a paired problem. So we only need one box plot, and the box plot needs to be of the differences of our data. So we don't need to look at the box plot for just the generic ice cream. We don't need the box plot for just the Breyers ice cream. We truly only need C, the difference of the melt times. Now, if, again, this was a two sample problem, then we would need to look at both box plots, the generic ice cream box plot and the Breyers ice cream box plot. So if it was a two sample problem, then we would need to take a look at answer choice D. Number 8, a Census Bureau report on the income of Americans says that with 90% confidence, the mean income of all U.S. households in a recent year was $57,005, with a margin of error of $742. Which of the following is the most appropriate conclusion? So 90% of all households, hold on. They're saying 90% confidence. So the confidence level is 90%. So when they're saying that the 90% relates to the population of all households here, incorrect. They are misusing what that 90% confidence level really means. B, we can be sure that the mean income for all households in the country lies in the interval. Now, basically, if we did the math here, we would create the confidence interval itself. But when they say we can be sure that the mean income, basically they're saying there is no doubt that the mean income is in this interval. And we can't be 100% sure is basically what they're implying here. So remember, we're only 90% confident. We are not 100% confident. C, 90% of households. Well, I can pretty much tell you that right now. This is not going to be good. D, the Census Bureau got the result, $57,005 plus or minus $742. So they're saying that they got this result of the confidence interval using a method that will capture the true mean income 90% of the time when used repeatedly. Now, this sounds great because the method that they're talking about is if they took, again, when they say when used repeatedly, if they did many random samples and they created 90% confidence intervals from all of those many random samples, then we would expect about 90% of those confidence intervals to do their job of capturing the true mean. So this one is sounding really good, but let's make sure that it's not answer choice E. 90% of all possible samples of the same size would result in a sample mean that falls within $742 of $57,005. They're making this one confidence interval that came from one sample sound so special about 90% of the population of samples. And again, that is just misinterpreting what that really represents. So I am confident, 100% confident, that the answer really is D. Number 9, a quiz question gives random samples of 10 observations from each of two normally distributed populations. Tom uses a table of t-distribution critical values and 9 degrees of freedom. Why 9 degrees of freedom? Sample size minus 1. For the difference in the two population means. Janelle uses her calculator's two-sample t-interval with 16.87 degrees of freedom to compute the 95% confidence interval. Assume that both students calculate the intervals correctly. Which of the following is true? So the 16.87 degrees of freedom, I mean, that sounds like a weird number for degrees of freedom. Remember, our calculator uses that crazy Satterwati formula, which is technically the more precise degrees of freedom. And Tom is just using the more conservative estimate of taking the smaller sample size minus 1. And it said that both of them were sample sizes of 10. So they tie smaller sample sizes the same, minus 1, 9 degrees of freedom. Now, what we had mentioned about the big difference between using the crazy formula and using the conservative approach is that the conservative approach of the smaller sample size minus 1 is always going to produce confidence intervals where the margin of error is bigger than what it really should be. The conservative approach, again, is meaning that we are going to have more values in our confidence interval than what we would have if we had just used the crazy formula. So for answer choice A, when it says Tom's interval is wider, Tom used the 9 degrees of freedom. And again, his margin of error is going to be larger. And if his margin of error is larger, then overall his confidence interval is going to be wider. So I can tell you right now, Tom's confidence interval is going to be wider because the margin of error is bigger, because the degrees of freedom were smaller. As our degrees of freedom got bigger and bigger and bigger, then we said that the critical value really gets smaller and smaller and smaller, and it starts to approach whatever the standard normal, the Z critical value would be for that situation. All right, and the last one. The makers of a specialty brand of bottled water claim that their mini bottles contain 8 ounces of water. To investigate this claim, a consumer advocate randomly selected a sample of 10 bottles and carefully measured the amount of water in each bottle. The mean volume was 7.98 ounces, and the 95% confidence interval for the true mean volume is 7.93 to 8.03 ounces. Based on the sample, which of the following conclusions best addresses the maker's claim? Now, remember, the maker's claim was that the mini bottles contain 8 ounces of water. Now, so this is kind of like a half confidence interval problem, half hypothesis test problem. And we haven't officially talked about hypothesis testing for means yet because that's next chapter. But based on what we have learned about confidence intervals and hypothesis testing for proportions, it's really the same idea, except we're talking about means here instead of proportions. So if we were to think about the null and alternate hypothesis in this situation, the claim being made about the population mean volume is that it is 8 ounces. And they didn't really specify that they thought maybe it was going to be smaller than 8 ounces, but I get the feeling that's what they were kind of going for. But if I look at my answer choices here at the end, they're just saying their claim is correct, incorrect, correct, incorrect, incorrect. So I guess since they didn't specify which direction, then I guess we should say for the alternate that it's two-sided. Plus, a confidence interval really only works great with a hypothesis test if it is, in fact, two-sided. So I think we're making the right decision here, that it should be a not equal to for the alternate hypothesis. Now, the confidence interval they came up with was 7.93 to 8.03. So we're really testing, is the mean truly 8? Well, is 8 in the confidence interval? And it is, in fact. So if you take a look at the first parts of these answers, because 7.98 is in the interval, well, I know 7.98 is the point estimate. That was the sample mean. It is the true midpoint of this confidence interval. So absolutely it's in there. That's how the confidence interval started to be created, was by the 7.98. So they're using the wrong value to explore in the confidence interval. But we're wanting to look at 8. So because 8 is in the interval, okay, so far C and D are looking great. Because 0 is not in the interval, well, we're only looking for 0 if it's a 2 sample problem. If we're looking for a difference, and this is a 1 sample problem, this isn't a 2 sample problem, so we're not looking for 0. All right, so because 8 is in the interval, then we have convincing evidence or we do not have convincing evidence. Well, if 8 is in there, then we would basically fail to reject the null hypothesis. And if we fail to reject the null hypothesis because 8 is still a plausible true mean volume, then we would state that there's not convincing evidence that the claim is incorrect. Mu equals 8 is basically saying the claim is correct, and the alternate hypothesis, mu is not 8, would be saying that the claim is incorrect. And remember, we're always trying to conclude in the end that the alternate hypothesis is what we're trying to go for. So it makes sense when they say that the claim is incorrect. Well, that's the alternate. Do we have enough evidence to go with the alternate hypothesis? And we said, no, we do not have enough evidence to support the alternate hypothesis. Why? Because 8, the null hypothesis, is contained in our confidence interval. And that is all. Good luck on the test, and eat Breyer's ice cream.